Okay, I think we're good.
Great. Okay, so thanks very much for the invitation to talk today. So I'm going to give a sort of selective overview of some topics related to this idea of explaining the anomalously high temperature of the sun's corona by so-called magnetic field line braiding. So I guess hopefully everybody's familiar with the idea that the sun's corona is about 3 orders of magnitude higher than its surface, and we need to somehow explain this. And some kind of part of this process is sort of, I guess, colloquially known as the Parker problem. So I'm going to go through a few different topics. Maybe I can just, so I'm going to go through a few different topics. At the start, it's going to be maybe a bit more theoretical, and then we'll get on to looking at some things that are more directly related to the observations a bit later. Obviously, I'm going to have to jump over a number of the topics here quite quickly. So all of this is covered in much more detail in this review article, the details of which are at the bottom, that came out in Living Reviews in Solar Physics last year. So we're going to start out by just stating what this, how this mechanism works, or what the hypothesis is. And I guess conceptually first, the basic idea is that we have convective motions in the photosphere and below, which will drag around the foot points of magnetic field lines that connect up into the corona. Now, because the corona has an extremely high magnetic Reynolds number, the evolution of the magnetic field and of the plasma up in the atmosphere will be ideal. That is, the topology is preserved. And so as the foot points of the field lines move around, they will tangle the field lines in the overlying corona around one another. And this tangling cannot in general be undone, or at least not easily. And so the hypothesis is that this tangled field, this field in which the field lines wind around each other in some complicated way, in general doesn't admit a smooth equilibrium, or that if you were to take that field and relax it towards an equilibrium, that equilibrium would be non-smooth or would contain current sheets. Current sheet is just is going to be used. I'm going to use that here to mean a finite amount of current flowing, but an infinite current density within a sheet of infinitesimal width. So this corresponds to a tangential discontinuity of the magnetic field at a surface. So then, as supposing that the field were to relax towards such a state, eventually, even for extremely high magnetic Reynolds number, eventually you would have to get reconnection occurring, and then this can allow the field to simplify its topology, it can release magnetic energy and generate heat. And so this part of the process, I guess, in the red box, is then what's known as the Parker problem. This is the hypothesis that the field doesn't have a smooth equilibrium. And to home in on that part of the process in a bit more detail, this is the kind of basic idea that Parker put forward. So the idea is to simplify some part of the corona into a geometry where you have field lines just running between two parallel, perfectly conducting plates. You suppose that you start out with an equilibrium magnetic field. Maybe it's a uniform field or something different. You now perform some displacement of the field line foot points on one or both of those planes, and then you stop the boundary perturbation, you stop the flow on the boundary, and you relax the field towards an equilibrium in the presence of some kind of damping, but you don't allow reconnection. And if you don't allow reconnection, then the topology of the field has to be preserved. So by topology here, I mean the linkage of the field lines with one another, the way that they wind around one another, as well as the way that they connect between the two boundaries. And then the hypothesis has been stated in a few different forms in the literature. We kind of, in our living review, split it up into these three definitions, although they're not formally written like this in the literature. So the definition one there is the most general form of the statement. It says that in the above setting, in almost all cases, so for almost all possible boundary flows or boundary deformations, then as the field relaxes towards a static equilibrium, the magnetic field will develop tangential discontinuities due to the absence of a static equilibrium that's smooth. So this is the kind of general form. This corresponds to a static equilibrium where pressure forces can balance J cross B. Now, to simplify somewhat, a number of people address the question, what happens if that final equilibrium to which you're approaching is a force-free field? So just J cross B equals 0, and that would be definition 2, that in the relaxation towards a force-free field, you develop tangential discontinuities. Option number 3 here is a somewhat weaker statement. What that says is that for almost all possible flows that have been applied on the boundary, as we relax towards an equilibrium, the field has to develop current layers. So here, the current layers are distinguished from current sheets. A current layer has finite width and a finite value of the current density. But this hypothesis is that the width of those current layers has to decrease and the intensity of the current density has to increase exponentially as the complexity of the deformation increases. Okay, and we'll look a little bit more at these as we go through the next few slides. So I'm going to start out by outlining a few of the theoretical arguments for and against the formation of tangential discontinuities of the magnetic field. So Parker's original argument was based on an infinitesimal perturbation away from a uniform field, but it was subsequently shown that there was an error in the original calculation, and that for infinitesimal perturbations from a uniform field, the field can always relax to a smooth equilibrium. So that's these papers by Van Ballenhoijn and Zweibel and Lee, for example, showed that for an infinitesimal perturbation, then we shouldn't expect to get to a state where we have current sheets. Now that leaves open the question, what happens when the perturbation is finite, is not infinitesimal, which would be a more realistic case. And that has, there's been substantial debate on that question without any real consensus. And why, I guess, we might like to understand why the problem is so hard. Well, the problem is so difficult to figure out mathematically because we need to solve the force-free equations while also precisely specifying or possibly maintaining the magnetic field topology. Now, the magnetic field topology, like I said, is related to the linkage of all the field lines with one another and the way they connect between the boundaries. And so therefore, by definition, the topology is a global quantity. It's not something that you can define locally. And so encoding that global topology of the field into the problem is challenging. Okay, so I'm not going to go through in great detail the arguments for and against. I'm just going to highlight a few of them here. So arguments in favor of the formation of tangential discontinuities in this scenario. Parker wrote a series of papers on what he called the optical analogy. These exploit the fact that the equation of a field line in a potential magnetic field is the same as the equation of the path of an optical ray, where in this analogy, the index of refraction becomes the magnetic field strength. And so there's a couple of sketches in the top right here of what happens if you consider a location of enhanced magnetic field strength, which is drawn with the lens type shape. And by analogy with the optical case, the argument is that the rays should take the shortest path and therefore should avoid maxima of the field strength. Now, if you have a sufficiently large magnetic field concentration, then you might have the rays or the field lines avoid this region altogether. And if you now imagine, which is the bottom figure, a kind of foliation of these flux surfaces, and you imagine that in some slab in the middle, you've got a bunch of flux surfaces where there's a hole in the middle, then the field from above and below the slabs, the field lines could touch across that hole and might not necessarily match. Okay, next up, there's an argument based on the uniqueness of equilibria. So Ng and Bhattacharjee in 1998 they exploited the fact that the reduced MHD equations are analogous to the 2D Euler equations, and they used that to prove that for reduced MHD, for any given foot point mapping that's smoothly connected with the identity mapping is what you have for a uniform field, then there's at most one smooth equilibrium. And so therefore, what has to happen if the smooth equilibrium loses stability, the field has to relax towards some lower energy state, which has to be non-smooth because there are no other smooth equilibria. So this works in reduced MHD rather than full MHD. There's also a series of papers by B.C. Lowe and co-workers on what they call topologically untwisted fields. So these are potential fields and fields that are potential everywhere except at cuts, at tangential discontinuities. Okay, just then highlighting a few of the arguments against the formation of tangential discontinuities. The most general result that we actually have on the existence of force-free fields is due to Binot almost 50 years ago. So in that paper, it was proved that force-free fields of arbitrary topology exist for sufficiently small alpha. So alpha here is the force-free parameter, as in curl B equals alpha B. And so this seems like we're nearly home, except for this part at the end, sufficiently small alpha. And the thing that is still missing from this is that we don't actually know, and the paper doesn't, or the approach doesn't give any insight into what sufficiently small means. So it's a finite neighborhood. It's not just for infinitesimally small alpha, but yeah, we don't know how far away from a potential field you have to get in terms of the amount of current, in terms of alpha, before you can no longer guarantee the existence of a force-free field. Arguments on the accessibility of solutions. So with tangential discontinuities. So it's clearly has to be the case in like a mathematical sense that the space of all force-free fields must be much larger than the space of smooth force-free fields. There's got to be lots of force-free fields with a non-smooth topology, and so the question is, or a non-smooth structure, and so the question is, can those be accessed in this geometry that's imagined by Parker, which is kind of consistent with the corona? That is, we start with a smooth field and we apply only smooth motions on the boundaries. So that in these various papers by Van Bellehuyn and Longcope and Strauss and Cowley, they give slightly different versions of this argument, which basically says that those non-smooth fields, we can't get to them if we only apply smooth boundary motions to an initially smooth field. And as a very rough sketch of how that proof works, they take a configuration like in the picture here, where you have the gray bar in the middle is supposed to indicate some hypothetical current sheet. This is a proof by contradiction. So you then consider two field lines, one on either side of the current sheet, which are just infinitesimally, their starting points are infinitesimally close to one another immediately on either side of the current sheet. Because the boundary motions are smooth, their endpoints also have to be infinitesimally close to one another on either side of the current sheet. So that's at z equals 0 and z equals L. And then because the current has to flow on the sheet in a force-free field, you can go through some algebra to show that basically the angle between those field lines, C1 and C2, has to be 0 all along the length of the sheet. Or in other words, that's a contradiction of the fact that there's actually a sheet there in the first place. So it's worth highlighting that this only works for a simple planar sheet, so a current sheet that just looks like a line in cross-section. And so people imagined some more complex type of current sheet structures for which this argument wouldn't hold. So there were also various computational approaches to seeking signatures of tangential discontinuities, which none of which found anything equivocal. And so basically, I guess to summarize the last two slides, we have no hard proof or counterproof of that tangential discontinuities or current sheets should generally form in this geometry that matches Parker's. So what I hope I'm going to convince you of in the next few slides is that actually this doesn't really matter if we're, for the sake of understanding the behavior of the corona, it doesn't actually matter whether we approach a state with genuine tangential discontinuities. Okay, so we're going to switch on to talking about some more computational results. Just one slide about the kind of philosophy of how this works. So generally, these simulations could be described as an ideal relaxation simulation. The philosophy of that approach is that you choose a topology that you're interested in. Maybe it's got tangled field lines. You specify a field with that topology at t equals 0. That's not going to be an equilibrium field, but you now want to minimize the forces or the free energy in your simulation to find a corresponding equilibrium while maintaining the topology. So that's important. You've specified this topology. You now have to exactly fix it. That means you have to completely exclude reconnection, which means that you typically need a Lagrangian grid approach to your computational scheme. So if you use an Eulerian grid, then there will always be some finite numerical dissipation, and so some finite slippage between the field and the plasma. Now, there are different ways to minimize the forces or the free energy. People used a so-called magnetofrictional approach or viscous damping. But the idea basically is that you want to look at the structure of the magnetic field or of the current density in the final state of your relaxation, in the energy minimum. And then if there is a current sheet in that magnetic field, then if you do a convergence test with the numerical resolution, so as you sequentially increase the resolution, then the current density should diverge if there's an underlying singularity. On the other hand, if the magnetic field is smooth, so if the current is finite, then the current value should converge with the resolution. Okay, so before looking at the results of such simulations, let's just do a little thought experiment on what we might expect to find. So let's imagine that we've got a magnetic field where the field lines are all braided or tangled around one another, like in Parker's model. And let's think about what kind of structure a force-free equilibrium would have to have. So let's suppose we have a force-free equilibrium, J cross B equals 0, or equivalently, curl B equals alpha b, where b dot gradient alpha equals 0, which means that alpha is constant along magnetic field lines. And now let's imagine that alpha has some distribution with a characteristic length scale, call it L, on say the lower boundary, the left-hand boundary in the picture at the top there. So now if we know alpha on one cross section and we know that alpha is constant along field lines, then we can just project alpha along the field and find the distribution, find out what the distribution of alpha is at any other cross section. And what happens if we do that? In this example at the top here, we've just taken not a real alpha, but just a linear gradient profile at the left-hand end from blue to red. And then we just project that along the field lines, assuming that that quantity has to be constant along the field lines. We project it along the field lines, and we see the pattern that we get at the right-hand end. And the reason that we have this complicated swirly pattern with all the red and white and blue swirled together is because the field lines are tangled around one another, and they carry the alpha value with them. So if we take this imagined distribution then with a perpendicular length scale L for alpha, and then we map it along the field lines, then in general, alpha has to exhibit length scales that are controlled by the field line mapping, by the way that the field lines wind as they go between the boundaries. And in particular, that length scale should be L times the smallest eigenvalue of the Jacobian of the field line mapping, which is lambda min. So we can quantify that in some way. So we've argued that if we have a tangled field, then we have to have alpha having small length scales in the direction perpendicular to the loop, somewhere in the loop. But then alpha is by definition just j dot b over b squared. And if we assume that that the field along the loop is dominant, then say b is of order 1, then alpha is just proportional to the parallel current to j parallel. And so therefore this tells us that not only alpha, but also the current must have small length scales. And not only that, but the length scales have to be smaller, the current layers have to be thinner for increasingly complicated field line mapping, or increasingly tangled fields. So we didn't prove that a smooth force-free equilibrium exists for a tangled field, but what we have argued is that if it exists, it has to contain current layers that are at least as thin as those layers in the field line mapping. All right, so to test this, we've performed a bunch of these ideal relaxation simulations. So what we've taken is a series of different starting fields of increasingly tangled or increasingly braided magnetic fields. And the way that we do this is through this construction here. The expression for the magnetic field is shown in the equation. The only important thing to notice is basically this parameter here, k. The parameter k basically controls the amount of twisting and tangling that the field lines experience as they travel from one end of the box to the other. And that's shown, we can show that visually by looking at some property of the field line mapping. For example, on a cross-section, that's what's shown on the right-hand side here. And what we're actually plotting here, which would be familiar to at least a number of solar physicists, is the squashing factor, which is just one way to visualize the field line mapping. And what we can see as we go from the top to the bottom is that if we increase our k parameter, then the peak value of that squashing factor will increase, and also we'll get many, many more of these narrow layers of Q of the squashing factor. All right, so what we're going to do is we're going to take a series of different initial magnetic fields, which are increasingly more and more tangled, and we're going to relax each of them towards an equilibrium and look at what the current density looks like in the equilibrium. So that's what we've done here. There are 3 different values of K, so going from left to right in these columns, we're looking at increasingly tangled magnetic fields or increasingly braided magnetic fields. That's shown by Q again in the bottom panel. And then the top panels and the middle panels are 3-dimensional views of the current density and then a cut through the midplane. And what we have is current layers that have a finite thickness, but that thickness is decreasing as we move from left to right, or in other words, as we consider increasingly complex degrees of tangling. So to double check that these are finite current layers, there's no underlying unresolved structure, we've made a scaling study with the numerical resolution to show that as we sequentially increase the resolution, those current layers stay of the same thickness and the current density stays of the same size as we continually increase the resolution. So then if we want to go ahead and try and quantify the thickness of those current layers, then we can take some kind of cut across them. That's shown with the white dashed lines there. And then we can measure the thickness of the current layer for the different simulations. And the current layer thickness as a function of our parameter that controls the complexity is shown in the left-hand plot here. So Wj is the current layer thickness, and approximately we fit this scaling law to it on the left. We can do the same thing on the right, but instead of measuring the current layer thickness, we can measure the thickness of the layers in the field line mapping instead, which I'm calling WQ, and we can put a fit through that as well. And what we find is that to within the errors of our fitting parameters, we have the same scaling, or something like, or approximately minus 2.4 here. And we have the same scaling for the current layer thickness and the thickness of the field line, the layers in the field line mapping. So hopefully this shows us a kind of realization of the fact that we have, of our thought experiment being borne out, that we should have current layers that are whose thickness is governed by the properties of the tangling, the properties of the mapping. So these are consistent with earlier studies by Van Ballehoijn and Mikic et al. Back in those days, they didn't have all of the mathematical development of things like the squashing factor, but they saw exactly the same thing, that as they made sequences of perturbations, relaxed the field in between each perturbation, and saw an increasing current density on increasingly small scales. So what do we conclude from all this? We conclude that for braided magnetic fields, as in Parker's scenario, we do have smooth equilibria, at least in the cases that have been so far looked at. But that these equilibria have to contain current layers whose thickness scales inversely with the braiding complexity. And so as a result, although this is not consistent with the kind of stronger forms of Parker's hypothesis, it is consistent with the weaker form. And what this means is that in the solar corona, as the field is continually braided up by the boundary motions, we have to inevitably have the onset of reconnection. Inevitably, the current layers will become thin enough and the current will become sufficiently intense that reconnection has to set in. And if we want to, we can use these scalings to try to extrapolate and figure out what sort of a degree of braiding we might expect in the corona. Now, there's there's difficulty in that we want to try and figure out when heating is going to start. And for that, we need to know an onset threshold for 3D reconnection, which we do not know. But we can make a conservative estimate by saying that we might expect reconnection to become dynamically important when the current layer aspect ratio gets down to the threshold for the plasmoid instability, nonlinear tearing, or maybe the current layer thickness has to get all the way down to the ion larva radius. Now, most likely, reconnection will happen before these, but this is just a conservative estimate. If we make this estimate and we put in some kind of typical numbers, then we get a fairly large free energy associated with our braiding, which is well above what you need for a single nanoflare. Now, of course, you would generally expect only a partial relaxation. You don't get all of this energy out at once. And that should be balanced by the energy input. Now, an obvious question that one might ask is whether this level of braiding that we're talking about here is in any way realistic, and I'll touch on that briefly a little bit later. But first of all, just mention a bunch of studies that looked at what happens in the real case where we do have a finite resistivity, where the magnetic Reynolds number is not infinite, it's not a purely ideal evolution. So there are lots of computational studies where people tried to address this braiding scenario by simulating it in a code with a finite resistivity, so you do allow reconnection in the current layers that form in the volume. And there are lots and lots of different approaches to this. Some of these apply the driving continuously from the boundaries. Others look at a relaxation process where the boundaries are not driven as the evolution occurs. There's also some studies that use the full set of MHD equations, but a lot that use reduced MHD, especially earlier studies. Different domain aspect ratios, some of which are closer in geometry to a coronal loop, and others are more like just a square box. Different driving velocities are used. There are a few examples of the driving patterns from some of those simulations shown at the bottom there. So I'm not going to go through all of these different studies, but just pick out a couple of examples. First of all, there's a series of simulations by Rapazzo et al., where they drive the simulation domain continuously from the boundaries in geometry like Parker's. We see the field lines there on in the top left panel. So the top and bottom boundaries in Z are continuously driven in these simulations. They solve the reduced MHD equations, and they've looked at various different forms of the driving. So now what happens in these continuously driven simulations is that the system eventually reaches some kind of statistically steady state where the energy that's being pumped in, or the field line tangling, is balanced by the energy dissipation and the reconnection, which helps to untangle the field. And we can see that this is a statistically steady state, approximately by looking at these plots of the magnetic and kinetic energy as a function of time in the bottom left. So then one of the main focuses of these studies is to look at the properties of this statistically steady state, which turns out to be turbulent. And so when there's focus on looking at how various properties depend on what the spectrum looks like of various quantities like the magnetic energy, and how that depends on things like the magnetic field strength, the length of the loop, and the driving timescales. So an alternative approach is to, instead of driving and relaxing the field both at the same time, you can take the field to a braided state and then allow it to relax, to undergo a resistive relaxation while the boundaries are held fixed. So that's what is done in these simulations here. there are 3 images of the current density at different times in the simulation that are shown. The middle one shows the formation of those 2 initial current ribbons that we saw previously in the ideal relaxation. Now, because the resistivity is finite, reconnection is allowed to happen in those current layers. And what we end up seeing is that once reconnection happens in the initial 2 current layers, it spawns a whole kind of fragmented structure of current layers eventually. And we basically have an evolution that resembles some kind of decaying turbulence. And then if we look at what the magnetic field lines are doing during this relaxation process, they basically unbraid themselves. So we start out with a situation where the field lines are wound around one another in a very complex way, and they basically unwind and unbraid themselves by the end of the simulation, and we have a much simpler and lower energy magnetic field. Okay, this is a very wordy slide. These are just some kind of main results, I guess, of these many flux braiding simulations that have been performed. So in general, when we apply the boundary motions in all the simulations, you form thin ribbons of current. The evolution generally is described as an anisotropic turbulence, either driven turbulence or decaying turbulence. And the scaling exponents, like I said, depend on different parameters. The magnetic energy tends to dominate the kinetic energy by a factor of at least 10, depending on which simulation you look at. So this is not equipartition in the turbulent cascade. And the geometry of the driving seems to have a fairly minimal importance, as if people looked at shear velocities or they looked at velocity profiles that were a series of vortices and so on. It tends to have a minimal importance, but some kind of global properties of that driving might be important. So for example, the helicity injection rate or the correlation time of the driving seem to affect some kind of overall characteristics of the energy release. There are, though, a bunch of outstanding issues. So most of these studies which are able to do any kind of scaling with the Reynolds number, most of them use reduced MHD. And for large magnetic Reynolds number, the B part tends to become larger to an extent where maybe RMHD is no longer an appropriate assumption. So understanding how the magnetic Reynolds number influences the things like the energy dissipation is still very important to try and address. There's also a question of timescale, so how the driving timescale compares to the timescale of the energy release. And then, obviously, the elephant in the room in all of this stuff, looking at this geometry proposed by Parker, is the fact that we basically stop our model at the top of the chromosphere. And so what the effect of the complicated plasma and magnetic field structure in the chromosphere and magnetic carpet is. Okay, so just going to touch on a few topics now related to the extent to which we can link some of these theoretical studies to the observations. So first of all, we had a question of whether these highly braided magnetic fields are in any way realistic. So can we expect the flows on the photosphere to really give us these very braided or tangled fields? So to try to address that in this paper here, we've looked at flows both from magnetoconvection simulations and those inferred using observations, as shown in the 2 movies. And the idea is that you can take those flows, those 2-dimensional flows, either from the simulation or from the observations, and you can turn that into a 3-dimensional braid by just imagining that your field line foot points are basically like corks in that flow. And so if you take the 2-dimensional flow plus time, that will show you the braiding pattern that's going to be induced on the field lines that are anchored in that flow. And we have a couple of different visualizations of the complexity of those flows. These are both for the magnetoconvection simulations. The left is just basically a paint stirring experiment using the flows. The right-hand side shows the same kind of patterns, but what's plotted here is the winding number. This tells us how the field lines wrap around one another. If you weight it by the flux, it's basically the helicity per field line. So without the time to go into too many details, these kind of analyses allow us to show that we would expect to achieve a state where the field is highly tangled, by which I mean tangled to something like the extent that we looked at in those simulations. If we were to start with a straight field, we would get there in about 10 minutes if we took the flows from the simulations to drive our field. On the other hand, based on the flows inferred from the observations, then this takes something more like an hour or so, depending on what method you use for your velocity inversion. Okay, another an argument that's sometimes put forward against this braiding hypothesis is that we don't really see, in general, bright features tangled around one another when we look in coronal observations. So, I guess counter such arguments, that we have these results from the simulations by Dalberg et al. They're basically similar to the continuously driven simulations by Rapazzo that I talked about above. We have tangled field lines that plasma is being heated by the braiding process in these simulations, but these synthesized emissions clearly don't show anything that you would look at and say, aha, that's some braided structure. So this shows us that we don't necessarily see the braided field when we look in the emissions. So we also looked at this at synthesizing emissions for the relaxation simulation approach. So these are this is just a snapshot from in the middle of a resistive MHD equation, where we have in the left-hand image the current densities in green, and we've got some magnetic field lines. And then on the right is some synthesized emission in iron 12 in this case. And what we don't see any obvious braided structure in that emission. Okay, so we've gone a little bit further in these simulations here and tried to assess whether the spectroscopic properties for what we can synthesize from our simulation are consistent with the observations. So what should we expect? What are the loop emission spectra kind of characteristic properties? Well, typically in the corona, we observe a non-thermal broadening on the order of something like 15 to 30 kilometers per second. And that's shown for different elements, different ions in the bottom left plot there. It tends to be approximately independent of the instrument resolution. In certain cases, it's been observed a correlation between the non-thermal broadening and the intensity of the line. And also, in general case, the line profiles tend to be non-Gaussian. So if we take the line profile and we fit a Gaussian, in general, there's enhanced power in the wings. So we wanted to see whether if we take one of our braiding simulations, whether any of these properties are also seen there. So I'm showing the results of simulations that are very similar to the ones that we did before, only that we now have thermal conduction and radiative losses, and then we've synthesized the emission for these simulations. And so what do we see? The top plot here shows the peak temperature and then the loop integrated emission, from which we basically see that the peak temperature rises and then falls, and the loop correspondingly brightens and then dims. In the bottom plot, in the blue curve, we see the magnetic energy. So that's showing us that we have this relaxation to a lower energy state. And we've also plotted the 1/E width of the synthesized emission line, which shows us where we have the 1/E width on the vertical axis there for the black curve. And so now what makes most sense is to take the situation where the loop would be brightest. So if we look at the top plot, the loop is going to be brightest between, let's say, roughly 100 and 200 seconds. And if we look then at what the non-thermal broadening is between 100 and 200 seconds, well, the total width of the line is something like 25 to 30 kilometers per second. And when we subtract the thermal width, we get a non-thermal broadening of something like 14 to 21 kilometers per second, which is in the ballpark for what's observed. So now we can dig into that in a bit more detail, and we can look not just at the spectra that we would get from integrating over the whole loop, but we can start to look at some different size viewing windows. So from left to right in these plots here, we're looking at the emission from the smallest white box on the right, the middle-sized white box, the largest white square box, and then on the very right-hand side is integrated over the whole loop. And I guess the first thing we see is that the broadening is roughly independent of the resolution that we choose, the size of box that we integrate over. And moreover, when we fit a Gaussian to the data, so the data is the black curve and the Gaussian is the red curve. When we fit a Gaussian to the data, we always see enhanced power in the wings in the data compared to the Gaussian fit. So it turns out that this is inherited directly from the velocity distribution, the velocities along the line of sight that are associated with that turbulent decay within the loop. So the bottom plots show just velocity histograms in those windows along the line of sight, and we again see that the data, the black curve, has extra power in the wings compared to a Gaussian. And this is known from studies of turbulence that this power in the wings is associated with intermittency in the turbulence. So we also, again, have correlation between the line width and the line intensity. And so we do seem to have these properties of the braiding that are self-consistently giving us the right spectral properties for a loop which is heated by this magnetic braiding process. All right. So in the last 1 or 2 minutes, just a couple of caveats. So the braiding model considers a single elemental loop. It can only be one part of the picture. Lots of things are excluded, like flux emergence, submergence, cancellation, and the complicated topology of the sun's magnetic field. So we know that the sun's magnetic field contains a whole array of null points and separatrices and quasi-separatrix layers, which are possible sites for the formation of current sheets. There are different models that look at what you have when you have heating associated with these separatrix surfaces. Priest et al. Have a flux tube tectonics model. This is sort of the opposite extreme from Parker in that they have all of the magnetic field concentrated in point charges on the surface rather than the field being uniform on the two planes. They still consider a case though where the polarity is we have all one polarity on one boundary and all the other polarity on the other boundary. When we include the mixed polarity of the photosphere, we have a whole plethora of nulls and separatoric surfaces in everywhere, and everything that can also be host sites for reconnection and for heating. This I think I have to skip over. And so active region, these large-scale active region models, they produce, I guess, the aim is to see to what extent the emission can be reproduced in these large-scale models. This is a recent example by Wernicke and Peter, where they took a time sequence of magnetograms to drive their simulation. And they do reproduce the large-scale structure and temperature, even though because of the resolution and cadence of the data and the simulation, the driving is slow, so it's some kind of DC type of heating. This suggests that reconnection does play some role in controlling what the distribution of the temperature is. What's always missing from these types of large-scale models is that the spectra don't match what's observed. You don't get the right non-thermal broadening, but as we saw above, this can potentially be explained by small-scale braiding, which is absent from these larger-scale models. All right, so to summarize, I guess if there's one take-home message from this talk, hopefully it's that the continual buffeting of the foot points by the photospheric flows has to inevitably lead to reconnection and heating. Whether there's really evolution towards a state with singular current sheets, I guess remains of mathematical interest. But basically, Parker's topological dissipation mechanism does work, and so seems certain to play some role in heating the magnetically closed corona, at least. Now, exactly what role that is remains to be seen, and we still need to understand a bunch of things about different processes in order to assess that. So, for example, the relation between the photospheric flows and polarities, how energy is transmitted up to the corona, the timescales for energy storage and release, and these issues that are hard to address computationally on how all these various processes that we talked about depend on the magnetic Reynolds number. So I'll stop talking now and happy to take questions and direct you to this review article for much more detail on everything I've said today.
Okay, thank you very much. Do we have any questions for David?
Hi, David, can I ask a question?
Yes, please.
Hi, thank you for your talk. I just was wondering, so you said when you were trying to calculate the synthetic line profiles, you were only looking through a finite width box. I was wondering if potentially, if you had some material in front or before, it may actually wash out. It may cause that, it may complicate how you interpret the line profiles.
Yeah, absolutely. I mean, this is, yeah, we don't even have a loop shaped box, right? We have a straight box. We've straightened our loop out. So I mean, there are a whole bunch of caveats, I guess, with that. We have looked at what happens if we look at different angles through that box, but I mean, fundamentally, we're taking an isolated box where we basically have like one loop maybe, or at least one kind of bundle of flux which is being heated and then cooling, but for sure, that would be complicated by anything in the foreground or background.
Great, thank you. And I guess the question was, you did show, maybe I didn't, maybe I missed it. Did you show actual observations with the enhanced wings?
I didn't know, but
I'll look at the review if they're in the review.
Yeah, so I actually don't think there's anything in the review, but if I go to, hopefully I've now put my screen up again. So Hardy Peter was the author on that paper who knows much more about the observations than I do. So if in this paper that's at the bottom of the screen here, bottom of the slide here, there are a bunch of references to the appropriate observations there.
Oh, thank you. Appreciate that.
Sure.
So I have a question, David, on possible future observations that might answer some of the questions that you finished up with in your summary there. I feel like in some sense, observational technology kind of moves to, we just try to keep increasing spatial resolution and temporal resolution. And I wonder if we keep doing that, will that answer your questions, or is there something fundamentally different that we need to try and observe?
I mean, I guess you're never going to get, or I mean, never is not accurate, but not in the foreseeable future are we going to get down to a length scale where we can really see like individual heating events. If an individual heating event is like a single current sheet, which reconnection in a single current sheet, which is not certain anyway, right? But let's imagine that it is. Then I don't think we're going to get there in the foreseeable future, right? On the basis of the parameters of the corona. I mean, the obviously enhanced spatial and temporal and spectral resolution can give us more detail, but I guess if the heating is turbulent, in which is what is shown in these simulations, but is also not, I guess, universally agreed upon. If it is turbulent, then I guess you're never going to see the bottom of that turbulent cascade, right? But you can still see a larger fraction of maybe the inertial range or something. So for sure, it can give us kind of more details, but I don't know that. I would hesitate to say, right, if you can get to resolution X, then suddenly everything is answered. I'm not sure that that's necessarily the case, which is maybe a bit of a pessimistic view, but.
Does anyone else have a question? All right. If not, then thank you again for a nice talk.
Thanks for having me.
And we'll see everyone else next week.